Welcome back to another episode of AI Talks with Chris and Nita. We're diving into a pretty cool area today, physics-informed machine learning. You might know it as PIML.
Yeah, it's where physics meets machine learning, trying to get computers to, well, think a bit like physicists would.
So not just crunching numbers, but actually understanding, the laws of physics. What could we do with that?
Huge potential. Think better aircraft designs, weather predictions that are more accurate, maybe even revolutionizing medicine, making it more personalized.
Okay, now I'm really interested. But there must be some downsides too, right? What are the strengths and weaknesses of this whole PML thing?
Of course. One big plus is it can work with less data, like way less than normal machine learning needs.
Why is that?
It's like they get a head start. They already know the physics, right? Say we're modeling how liquid flows. A regular model needs tons of data points to figure it out, the patterns. But a PML model, it uses fluid dynamics equations, learns way faster, even with just a little bit of data.
That makes sense. Less data, faster learning.
Okay.
So what's the trade-off?
Extrapolation. Inside the data it's trained on. Great predictions. But outside that, gets tricky.
Like students who ace tests but struggle with a brand new problem.
Exactly. Like self-driving cars, they need to handle things they've never seen, a sudden obstacle.
Those edge cases, right?
Yeah, and there, extrapolation is key. For those cars to be safe, tons of data, especially of those rare events. And even then, no guarantee.
So big hurdle for PML. Is there research on how to, get past that?
Oh yeah, lots of it. One way is to use even more advanced physics, give the models a deeper understanding of how things work.
Not just basic stuff, then.
Right. And there are hybrid models, combining PML with other things like deep reinforcement learning.
Combining the best of different AI approaches.
Exactly. This is letting us tackle harder problems, make the models more accurate and reliable.
Fascinating stuff. Sounds like PML is already being used in lots of areas. Can you give us some examples where it's working really well?
Sure. Fluid dynamics is a big one, like predicting weather, understanding ocean currents, designing more efficient airplanes, really complex stuff, and the old ways of simulating them. Slow and expensive.
So PIML could give us answers much quicker instead of waiting for supercomputers.
Exactly. And because it's using those physics laws, the simulations are fast, and they make sense physically. That's key for good results.
You wouldn't want a weather forecast that ignores physics.
Definitely not. Another promising area is drug discovery. Huge number of potential drugs out there, like finding a needle in a haystack.
Yeah.
PML can help narrow it down, predict which drugs will likely work best, based on their physical and chemical properties.
Like having a super scientist analyzing tons of possibilities in seconds.
That's a great way to put it. And this could mean new life-saving drugs way faster than before.
So we've got PML helping with climate, aircraft, maybe even new drugs. Huge impact already.
It is. And as it keeps developing, expect even more breakthroughs.
That's exciting. We talk about PML in general, but there are different types, right? You mentioned hybrid models. Can you tell us more about them, what makes them unique? I'm particularly interested in those physics-informed neural networks, the PNs.
Sure. PNNs are really cutting edge, combining the adaptability of neural networks with, the rigor of physics equations.
Best of both worlds. Learning power of neural networks and the accuracy of physics.
Exactly. They embed the physics right into how the network learns.
Sounds pretty technical. How does a neural network even UUC physics equations?
Imagine it's trying to learn how a fluid flows. A normal one might just connect data points, find patterns.
Just correlations, not the cause and effect.
Right, but a PNN, it also knows those fluid flow equations, so it's not just connecting dots, it's making sure those connections follow the laws of physics.
Like a physics teacher checking their work.
Exactly. This helps in a few ways. More accurate predictions, especially when data is scarce, because even if data is missing, it uses its physics knowledge to fill the gaps.
That's amazing. So PNNs are more robust, reliable, because they're grounded in physics.
Yes, less likely to make impossible predictions. They're showing great promise in tons of areas, from predicting how materials behave to modeling how diseases spread.
So PNNs could be game changers in fields where accuracy is super important. But I guess there are challenges in building and training them.
Of course. One big one is getting that balance right between fitting the data and following the physics equations. If it focuses too much on the data, it might end up with an answer that's physically impossible.
Like a student who crams but doesn't understand.
Yeah. But if it focuses too much on the equations, it might overfit and not work well with new situations, like memorizing a textbook but not knowing how to solve a slightly different problem.
Okay, I see the problem. What else is challenging?
complex geometries, like irregular shapes, complex interactions at the boundaries. Think airflow around a wing or blood flow in a heart. Not easy to incorporate that into PNNs.
So simpler systems are easier to model.
Exactly, and computational cost. As we model more complex things, the computing power needed goes way up.
So we need better computers, better algorithms to really use PNNs to their full potential.
Absolutely. And researchers are working on both. New hardware, more efficient algorithms.
So it's not just the models themselves, it's also the tools we need to use them.
Right. And having the right expertise. PIML needs people from physics, math, computer science. Needs collaboration.
A truly interdisciplinary field.
Absolutely. That's key for progress.
It sounds like there are big challenges, but lots of cool research happening too. What are some of the most promising areas you're seeing in PNN's research?
Hybrid models, for one. Combining PNNs with other things like deep reinforcement learning to make even more powerful models.
You mentioned them before. Can you give an example of how that works, like practically?
Say you're designing a robot to move around a complex environment. You could use a PNN for the physics of its movement, how it deals with gravity and friction, and use deep reinforcement learning to teach it to make decisions, like the best path to a goal. Combine those two, and you get a robot that's both realistic and smart.
So it understands physics AD, it can learn and adapt.
Exactly. Another area is interpretability. We talked about transparency, right? We need to understand how these models make decisions, especially for important applications.
We can't just trust a black box, especially if it's making decisions that affect people's lives.
Right. So they're developing ways to visualize what's happening inside PNs, see how they're using that physics knowledge, explain their predictions in a way we can understand.
So making AI more like human experts who can explain their reasoning.
Exactly. It's tough, but essential for trust and using them responsibly.
It's amazing to think we could have AI that not only solves problems, but explains how in a way we get it.
It really is a fascinating time to be working in this field.
I bet. We've talked about challenges, promising research areas, but what about actually using them? Where are PNNs already successful, and what could we see in the future?
Oh, tons of them. Like finding that sweet spot, fitting the data, but also sticking to the physics. If it's too focused on the data, the answer might not even make sense physically.
Like it finds patterns that aren't really there,
Yeah.
based on actual physics.
Exactly. But too focused on the equations, it might overfit, you know? Work great on the data it's seen, but not on new stuff. Like memorizing the textbook, but can't solve a new problem.
Ah, so it's a tough balance. What else is hard?
Complex geometries, like weird shapes, how things interact at the boundaries, like airflow over a wing or blood flow in a heart, not just a simple box. Hard to put that into PNNs.
So simpler systems are easier to work with.
Yeah, for sure. And computational cost is a big one. More complex systems, more data means needing a lot more computing power.
So better computers, more efficient algorithms.
Yeah.
Those are needed to really unlock what PNs can do.
Absolutely. And that's where a lot of research is focused, new hardware, new algorithms.
So it's not just about the model itself, it's the whole ecosystem around it.
Exactly. And having the right people. PML needs physicists, mathematicians, computer scientists, all working together.
Truly interdisciplinary.
Yeah, that's how we make real progress.
Sounds like some serious challenges, but also some really cool research going on. What are some of the most promising things you're seeing in PNN's research?
Hybrid models are really exciting. Combining PNNs with other stuff like deep reinforcement learning to make them even more powerful.
You talked about those before.
Yeah.
Any practical examples of how that works?
Sure. Imagine you're building a robot to move around a difficult environment. You could use a PN to handle the physics of its movement, how it interacts with gravity, friction, all that.
Okay.
And then use deep reinforcement learning to make it actually intelligent, make decisions like finding the best path to get somewhere. Combine those, and you have a robot that's both realistic and smart.
So it's not just following physics, it's learning and adapting too.
Exactly. And another big area is interpretability. We talked about transparency, being able to understand how these models make decisions, especially when the stakes are high.
Right, you don't want to just trust a black box, especially if it's making decisions that affect people.
Exactly. So researchers are working on ways to visualize what's going on inside PINNs, to understand how they're using physics knowledge, and explain their predictions in a way that makes sense to us.
Making AI more like human experts who can explain their reasoning.
That's the goal. It's a tough challenge, but it's essential if we want to trust these models and use them responsibly.
That's incredible. AI that can solve complex problems and explain how it did it in a way we understand.
It's a pretty exciting time to be working on this stuff.
I can imagine. So we've talked about the challenges, the exciting research, but what about real-world uses? Where are PANs already being used successfully, and what are some things we might see in the future?
PANs are being used in a lot of places already. Fluid dynamics is a big one, designing better aircraft wings, modeling how pollution spreads in the air, even predicting tsunamis.
Wow, those are some pretty serious applications. What about other areas?
Material science, designing new alloys with specific properties. Healthcare, personalizing treatments for patients. Even finance, trying to predict the market.
It's amazing how many different fields are using this. What about the future? What applications are you most excited about?
One that has huge potential is scientific discovery. Imagine using PNNs not just to model what we know, but to discover new physics.
Wow.
Like analyze data from experiments and find patterns that point to new laws of physics, things we haven't even thought of yet.
So PNNs could actually help us understand the universe better. That's incredible.
It is. And they could even help design better experiments, figure out what areas are most likely to lead to new discoveries, speed up scientific progress.
That's really exciting. But with all this potential, there must still be some big challenges to overcome before PNs can really revolutionize these fields, right?
Oh, absolutely. Scalability is a big one.
Yeah.
As we try to model more complex systems, use more data, the computational power needed just explodes.
So we need those better computers, better algorithms like we talked about before.
Exactly. And that's a big focus of research right now. New hardware, new algorithms that can handle these massive calculations.
Makes sense. What other challenges are there?
Dealing with uncertainty. Real-world data is messy, it's incomplete, and that can really mess with PMs. We need better ways to deal with that and still get reliable results.
So it's not just about the models, it's about how we handle the data too.
Exactly. That's why collaboration is so important. We need physicists, computer scientists, statisticians, all working together to solve these problems.
So that interdisciplinary approach is key for the future of PNs.
Definitely. That's how we'll push the limits of what's possible with this technology.
This has been a fantastic deep dive into the world of physics-informed machine learning and PNs especially. It's amazing to see how it's combining physics and AI to solve real problems, and it sounds like the future is even brighter.
I agree. We're just scratching the surface of what PNs can do, and I'm excited to see what happens next.
Thanks so much for sharing your insights with us. This has been a great conversation.
My pleasure.
And to our listeners, thanks for joining us on this deep dive. We hope you enjoyed it. Until next time.